Will I share my screen?
Okay.
Is that okay?
You can share your screen.
It's good. Can you see this?
Yes, but yes, that's in presentation mode now. Thank you so much.
Okay, great. Thank you very much for the introduction. I'm very, very happy to be here. I was recommended for this by a colleague of mine, Luis Pereira, who spoke very highly. So I'm working in Cinemat in Lisbon, and a lot of the work that I'm going to show to you today is work that I've done in Trinity College and I've extended over now on a Marie Curie fellowship. So I think it'd be good to just kind of give a broad general background on 2D materials themselves. And to do that, obviously, I need to begin with the prototypical 2D material, which is graphene. So I'm actually at Graphene Week, a conference here at the moment, which is in Prague, and this started 20 years ago when this material was first exfoliated and produced. So Nyman, Gaiman, Novoselov, they won the Nobel Prize not for simply exfoliating graphene here, but they also patterned it with electrodes and they showed that it has all these amazing properties. And ever since then, people have been trying to find applications for this. So at the moment, most of the commercial applications that have been found in are in things like composites. So we're seeing things like graphene put into motorcycle helmets. Sometimes it's in tennis rackets or the bodies of cars. Now, it's kind of funny because this material has been so hyped. Very often, one year we will see an article come out and say graphene is very far from the much hyped killer applications. And then a few months later, somebody else will publish an article saying it's meeting all the expectations. So, I mean, there's a lot of hype surrounding this material quite famously. So today, I think I want to answer the question, what is the big deal about 2D materials and why should we care about them? And the way I'm going to cover this is in four areas, covering everything from synthesis, creating inks and how to deposit these inks. And then once you deposit them, what are these networks like, these networks of nanosheets? And then I'll finish up speaking about a few devices. So beginning with synthesis and the materials themselves. So as I'm sure you've probably heard over the course of this school, we have these 2D materials, these layered crystals, these van der Waals structures. They're composed of lots and lots of different elements. I believe the latest number is something like there are 5,000 combinations of elements that give us 5,000 different materials. So we can find these anywhere. We can synthesize them. We can mine them out of the ground. We can find them in beaches and forests. They come like a crystal, which when we look inside, they're often these 2D layers. So graphene is shown here, which is a hexagonal lattice. However, if we take something like boron and nitrogen and alternate the sites in this hexagonal structure, we'd have boron nitride, which is an insulator. We have MOS2, and also we have structures like phosphorine. So with all the range of different elements that we have and the range of different structures, this means we have lots and lots of different properties. We've conductors, we've semiconductors, we've dielectrics, thermoelectrics, the whole lot. So basically, anything that we would want to use as a property to make something like electronics, I think we have it all here in this 2D family. So what's really special about these is that the properties change as you peel away the layers. So we take a bulk crystal like graphite, for example, and then as we start working our way down, the properties of the material, they change. So for example, with something like MOS2, a semiconductor, as you bring down the number of layers, the band gap changes. So we have tunability in here with layer number. Also, the band gap can change from direct to indirect. So as you go down, so this also gives us opportunities to work with light properties, optical properties. The mobility changes, of course, as you go down in layer number from tri-layer, bilayer to monolayer because you have screening and scattering effects. And then, of course, the elastic stiffness or the Young's modulus will change too because, you know, it's much easier to bend a single card than it is to bend something thick. So how do we make these? There's lots of different ways to make these. And over the past 20 years, people have explored a range of different ways, all with different strengths and weaknesses. So we have the top-down synthesis methods, where we start with a crystal, and then we do something to remove the layers one by one. And this leaves us then with the monolayers. We synthesize them that way. The way that this was done initially in the first paper was with micromechanical cleavage using the Scotch tape method, as it's known. Other ways to do it involve using light or solution processing, which I'll speak about a bit more later. Now, the bottom-up synthesis methods as well are where monolayers are grown. So you take some substrate like silicon carbide or metal substrate, and then you do something, you deposit these elemental precursors onto it, and this allows you then to form, to grow monolayers. Now, I'm going to talk to you today about the solution-based methods because these are I think we want to work with to generate lots and lots of material. So this is a high throughput method. And also this is a good way to make large area networks for devices, as I'll discuss. So the two most common solution processing techniques are known as liquid phase exfoliation, where we apply sonic energy into a solvent with a crystal in it, and this will then fragment and exfoliate our material. And then another way to do it is with electrochemical exfoliation, where we intercalate ions in between the layers of the bulk crystal, which then facilitates delamination. So I'm going to speak about this one first, which is the one that I spent most of my PhD in work on. So we take a sonotrode or a sonic probe. We take some solvent. IPA, for example, works. Water also with surfactant. And we take our layered crystal, our powder, and we put it in at a certain concentration. And then once you turn on this sonotrode, we get all these effects that go on. So you get all this transfer of energy from the tip. But this causes exfoliation and fragmentation via edge effects with interactions. We get fragmentation of our nanosheets, breaking them up. There is stress transfer then from the formation of bubbles and the collapse of those through cavitation. This transfers stress to the nanosheets, breaking up the crystal, and then they shear apart as well. So this is a very mechanically aggressive method for just breaking apart the crystal into monolayers. So we do this with a powder. We apply this sonic energy, and then at the end of this process, if we choose our solvent well, we will have a stable dispersion. But if it's a poor solvent, for example, like if you try to exfoliate graphite in IPA using this method, what will happen is it will all just reaggregate. So we need to match the parameters of our crystal with the parameters of our solvent. Now, the beauty of this technique is that it works for pretty much any material you can think of. There's no electrical limitations on this. And when we apply this process to any of these crystals and look inside, what we find are nanosheets. And what's important to note as well is that when we look at the basal planes, for example, of these exfoliated nanosheets, we find that they're generally quite pristine. So it doesn't induce any damage into the basal plane itself. Now, this technique is also scalable. We can use shear mixing then, which allows us to process liters per hour of this, which we just take a shear mixer, we take our material again, and what this does is that it applies shear effects into your dispersion, and then we can do this then on the scale of tens and tens of liters. So this is the commercial process that people generally use for creating large amounts of commercial material. So the thing is, once you break up this crystal, you're going to end up with nanosheets of all different sizes and lengths and thicknesses. So the question then is, what do we need to do to screen out the different sizes? Well, there's a number of ways of doing this. One of them is sedimentation-based centrifugation, where we just basically speed up the effects of gravity in a centrifuge, and we run our dispersion. And what will happen is, if you run it at a certain speed, nanosheets that are large, for example, will be sedimented out at the bottom of the vial, and smaller nanosheets will be left up the top. Another way of doing this is using a graded density solvent, so a solvent with lots of different densities. And then when you apply centrifugation, the nanosheets will actually sit inside of the layers in between each of the interfaces. And another one then, which is very similar to this, is just by using buoyancy. Now, as you can imagine, these two using density and buoyancy are they're quite difficult to do, because if you want to extract your nanosheets out of this layer, it's actually quite diffuse, these layers, they tend to be between the interfaces. So the easiest way to do this is just by using sedimentation. Now, this is a method known as liquid cascade centrifugation. So we will take our sonicated material, we will run the centrifuge at a low speed, for example, 1.5 kRPM. Then at the bottom of our vial, we will have all of the thick, unexfoliated sheets. So what we'll do is we'll just throw them away, we'll get rid of them. and then we will take the supernatant and centrifuge that at a higher speed. Then what will happen is we will get the sediment here, which will have this will give us a massive material with a fixed lengths and thicknesses. We will take this and keep it for processing, and then we can continue this process, taking the supernatant, taking the sediment, and work our way up, getting a range of different lengths and thicknesses. So yeah, as I said, this technique works for any layered material. This is great. It doesn't matter what the electronic properties of the material are. We can do it with graphene, we can do it with talcum powder, we can do it with tungsten disulfide, platinum diselenide, all of them. But what we do find with this process is that the thickness of the nanosheets is related to the length of the nanosheets. So this means if we want to get large nanosheets, they're also very thick. And if we want monolayers, for example, they tend to be very, very small in lateral size. So that's just one of the things that we have to deal with using this process. So this technique is extremely versatile. We published a paper here where we got talcum powder from a supermarket. We got cat litter also from a supermarket, which is an aluminosilicate. And the PI that I worked for, he had his kids dig up some sand at a beach, and we brought this into the lab. We applied this liquid phase processing technique. This is the SEM of the material as we picked it up, and we applied these techniques, and we got nanosheets out at the end. So this doesn't really matter where the material comes from, what it's composed of. As long as it's a layered crystal, we can apply this process to it. Now, something that's also come out of this is we've tried to demonstrate that this is usable, this is doable through just many methods. You can do this at home. And Connor Boland published these papers on hometronics where they take things like graphite from a pencil, you get tap water, you take something like soap as a surfactant, a kitchen blender to break it all up, and then coffee filters. And then he took just glue that you have in the house and used this to make pulse sensors. So this is very, very versatile technique, and it's cheap and it's scalable. Now, the other technique that I mentioned is electrochemical exfoliation. So this works by taking a crystal itself, you attach it to an electrode, and then you have a counter electrode, which is something like platinum or graphite. And then you apply a potential to your crystal, and you use this to drive ions in between. So what this does is that it widens the intersheet layer in between the nanosheets. And then when you apply just bath sonication for a few minutes, because these layers are now electronically decoupled, they will very easily exfoliate inside of a material. So this was first done back maybe 10 years ago with lithium, for example, because this is a very, very small ion. However, the problem is when you use lithium, you get an awful lot of these lithium ions. You get lots of them that go in between the layers. And what happens is, because of the charge transfer from the lithium to the crystal, you actually get a change of phase. So if you have a material like molybdenum disulfide, for example, this will convert from the 2H phase to the 1T phase, which means you no longer have a semiconductor, you have a conductor. So this is no good if you're trying to use this material to make things like transistors. You want a semiconductor. So these guys, Lin et al. In Nature in 2019, they decided to use a larger ion. So they use one of these tetraalkyl ammonium ions, which are quite bulky. So they have a diameter which is about 10 times larger, which means there are fewer ions intercalated into the crystal, which means there's less charge transfer. And when you use this ion here instead of lithium, what you find is you retain the semiconducting character as represented here by the photoluminescence, which only occurs in monolayer semiconducting MOS2. Now, this technique, because we need to apply a potential to the crystal, it only works on semiconductor conducting layered materials. So we're restricted here with the crystal needs to be conductive, but what the difference is, the nanosheets or monolayers that you get with this method, the nanosheets are huge, they're much, much bigger. The monolayers are huge, far bigger than we get with liquid phase exfoliation. So I've mentioned these nanosheet sizes. How do we find out about the size of the sheets? Well, TEM and AFM statistics are usually the way you do it. So you have some poor PhD student take all these images and then count about 200, 300 flakes. And this will give you a distribution of the sizes of a given sample. Now, this is quite laborious. So another way to do this is with UV-vis spectroscopy. And what we found was with a material like MOS2, for example, the excitonic features like the A exciton, these are related to the size of the nanosheets because of confinement effects around the edges. And what this does then means we can just quickly take a dispersion after it's been sonicated. We've applied our size selection techniques. We can do a UV vis spectrum, and this can tell us if we take something like the exciton location position, we can correlate this then with the length of the nanosheet. And this then allows us to do things like tune the band gaps and allows us to tune excitonic features. So we can very quickly get information about the size of the nanosheets. So I've shown you these two techniques. As always, every technique has advantages and disadvantages. The liquid phase exfoliation technique is high throughput. It's very, very good for scaling. We can create lots and lots of materials. But the drawback, as I'll tell you, is because the nanosheets are either small and thin, so monolayers tend to be very, very small, or they tend to be large and thick, so kind of bulky. With electrochemical exfoliation, we get very, very large area monolayers. So if you're skilled with your technique, you can get up to 75% monolayers in the dispersion at the end. But as you can imagine, the throughput is far, far lower. So the one thing to take away from this, if we're thinking about throughput versus aspect ratio, liquid phase exfoliation has a low aspect ratio, generally somewhere in the range of about 50, but we have a high throughput. Now, the low aspect ratio means you have a high surface area in your printed networks, which is good for things like battery electrodes where you want surface area. When it comes to electrochemical exfoliation, we have a very high aspect ratio of the range of hundreds to thousands. And this is very, very good for transistors because we have large basal planes. So the key points for the synthesis, these materials are easy to process. We have very, very high tunability across them. The liquid phase exfoliation technique itself works for any layered material. We have high throughput. However, we get a low mass of small monolayers. Electrochemical exfoliation gives us large area monolayers, but it only works with conductive materials. So moving on now to once we've made these materials in a solution, what can we do with them? Well, what we'd like to do is to be able to print them, because with printing you have low material loss. We get to pattern our electrodes, and it's already a scalable process that's used by industry. Now, usually to make an ink, you will take your dispersion, which will contain polymers for stabilization, perhaps, or to control the viscosity. You'll have surfactant to affect things like surface energy. You will choose an appropriate solvent, usually one that can evaporate very quickly after it's been printed. And then you will take your active material, which you will have size selected previously. We also have a lot of tunability here. We have a dilute ink for processes like inkjet printing, and then concentrated inks for things like screen printing. So the properties of these inks are very well understood because inks have been around for a long time. The properties that are important to us are, in particular, the wetting. We would like to have wetting that forms networks in a way where the droplets form continuous networks, for example. Depending on the viscosity of the ink, the deposited droplets will form different shapes, and the viscosity needs to be very well tuned to the deposition process itself. Now, when you're working with dilute inks, like the inkjet printed inks up here, we get problems with droplet evaporation. So as the droplets evaporate at the contact line here at the edges, anything that's contained within the droplet itself will tend to migrate towards the edges. So this is known as the coffee ring effect. And you don't want this because you don't want all your active material just at the outside of the droplet. What you would like is a continuous network where it's homogeneously deposited. So this is a problem that you need to monitor by using things like binary solvent systems or just by tuning with your surfactant. Now, what we also found is that the viscosity itself is tunable with nanosheet concentration. So when we're adding in these nanosheets, what we find is that above a certain concentration, the viscosity starts increasing by orders of magnitude. Now, this is good because it means we can just add in more active material, and we don't need to use as many polymers, because when you polymers in your network, you also need to get rid of them after they're printed. So stabilizing your material within dispersion can be done by surfactant, where we have these chains which will bond to the surface of the nanosheet, to the basal plane, and then you will have electrostatic repulsion preventing them from reaggregating inside a dispersion. Another way to do it is by polymer adsorption, where we add in a polymer to our dispersion, and this will adsorb on top of the material, and we'll have steric repulsion, preventing the nanosheets from coming into contact and reaggregating. Another way to do it then is also by solvent matching. So you take the surface energy of your solvent and you try to get it as close, you try to take a solvent with a surface energy as close as possible to the surface energy of your material. And what this means is that there is no energetic reduction when the material comes together. It's happy to stay in solvent as it is reaggregating. Now, this is probably the best way to do it for trying to make devices because the stability that you provide must be non-covalent to preserve the pristinity of the material, and any residue must be removable because once it's printed into a network, we want to make sure that the only thing in the network is our active material. So we take things like solvents. This is the surface energy of a solvent versus the concentration after we apply these techniques. This is for graphene. And what we find is that certain solvents give us much more exfoliated material compared to others. So when you take graphite and you just apply liquid phase exfoliation techniques, if you do it in water, we don't really get any material at all because water is a bad solvent for exfoliating in. We find something like NMP or a bunch of different solvents in here like CHP, and they're quite good. So what you want to do is choose one solvent and then use it to exfoliate your material. So then at the end, once you've printed it, you can remove the solvent and all you're left with following printing is your active material. So another way to do this is with a binary solvent system as well. So this gives you then tunability in surface area or surface energy because you can just mix in different amounts of, for example, water and ethanol. And it's funny, what we found was we read this paper where they found the optimum is in around 40%. So 40% ethanol, 60% water. And we thought that this was pretty curious because I think we're all quite familiar with solvent systems that have 40% ethanol and 60% water. And we decided to wonder, will this actually work with commercial whiskey, for example? So we went down to the supermarket, we bought some whiskey, and we tried to apply this process. And what we found was, yes, of course, the 40% water ethanol to water worked, and the whiskey compounds themselves that leach in from the barrel during the maturation process, this actually provided even more benefits of stabilization itself. So this allowed us to create what we called whiskey phase exfoliation. So the point of this was just to demonstrate the versatility of this technique. So we have these inks. This is great. Now we have our material. How do we deposit them then? Well, we have high throughput methods like the roll-to-roll flexographic methods, which allow us to produce high areas. Generally, the resolution of these tends to be a bit lower than what we can achieve with something like aerosol jet printing, where we can get extremely fine feature sizes, but the cost of that is obviously a very small nozzle, so you pay the price then with your throughput. So we need to decide what the trade-off is. Are we looking for high throughput or are we looking for high resolution? So I want to give you some demonstrations of the inkjet printing, the early graphene inks. So this was taken using NMP. They just exfoliated the graphite in NMP and then they just printed it as is. So this would have been just a vial, graphite and NMP, and put in a sonic bath for a range of time and then centrifuged once to remove large unexfoliated material and then printed using a Dymatics printer. And what they found was this worked very, very well. This was done by Max Lemme's group in 2013. And of course, because everybody was trying to make transistors out of graphene at the time, they tried to gate it. It didn't work very well, but what they found was that it made excellent electrodes for supercapacitors. So a couple of years later, or a year later, David Finn and Jonathan Coleman's group came along and they applied the same process, but instead of just taking graphene, they took MOS2, also generated, synthesized using these techniques, and they printed lateral structures where here you can see the black graphene electrodes, and then in the middle, the interdigitated channel, they put MOS2, and they showed that even over long distances of 1 millimeter with this material, they were able to get quite good functional photodetectors. So everybody was trying to make transistors. They were trying to, because graphene has high mobility. So the question was back at the beginning, how do we access this? How do we exploit it? So Felice Torrisi in 2012 inkjet printed graphene onto silicon dioxide wafer. They were able to gate it. Well, I mean, there was an on-off ratio of about 10, which is not bad, I would say, for a zero bandgap semiconductor. And they showed a mobility of about 95. So to improve this, what they did was they inkjetted in an organic semiconductor. And what this did had a doping effect, but you're introducing a polymer into the network, which meant you are going to reduce the mobility, unfortunately, but it had the effect of allowing the device to switch off. So this was also tried by, again, Max Lemon's group in 2014 with MOS2. MOS2 is inkjet printed onto a silicon dioxide wafer and backgated this way. However, they got this very ugly transfer curve, which is, well, I would say they're not actually gating the material at all. This is probably just a background capacitive effect. So instead, they just shone a light on it, and they showed it was also, it's MOS2, it's quite a good photodetector. So we printed these materials. What do the networks look like? Well, we've an inkjet printed network here. What we can see is the nanosheets are quite obvious. There's quite a lot of holes in here as well. The porosity is quite high. And if you look at a screen printed network, it's very, very hard to see the nanosheets. Okay, so the deposition method clearly has an effect on the structure of the network itself. If we look at the conductivity as a proxy for the quality of the network itself, what we notice is that since these papers started being published back in about 2012, regardless of deposition method, inkjet printed or screen printed, the conductivity is trending towards the graphitic basal plane. So we've all these improvements in conductivity, and it doesn't matter which way you deposit it. And this is because if we look at it, after you printed and deposited your network, the post-processing is really important. So this is a screen printed network of graphene. And this is done by Arapov et al. And what they found is a conductivity of their network of about 800 Siemens per meter. That was after 100 degrees annealing in the screen printed network. They applied photonic annealing, which actually, because of the volatilization of the polymers that were in there, the network got much thicker, but the conductivity still increased, which is very, very interesting. They then compressed the network to annihilate all of the pores and porosity. So it became much, much thinner. And this had the consequence of increasing the network by conductivity by about an order of magnitude. So the post-processing is really what counts here. What do you do with the network after you've printed it? So the alignment, the compression there, as we saw, is very, very important. What we want for high performance of conductivity, for example, or mobility, is a network with nanosheets that look like this, and not a network with nanosheets that look like this. So how do we what's the best way to make these highly aligned networks? Well, one way to do it is by spin coating, where the shear of the spin coating will mean you get a very, very good alignment of your sheets on top of a substrate like silicon. This is a very quick method and it's well established, but the downsides are if you only have a small amount of material, the last thing you want to do is throw it into the sides of a spin coater. So it's very, very wasteful. Another way to do this is what we've developed is using a liquid-liquid interface. So you take something like water and hexane, which have very different surface energies, and then you inject your nanosheets into the interface between these two solvents. And then these nanosheets will form a network along the interface. And if you do something then like pump out the solvents, you can deposit this network onto a substrate. And if you look at this network, you get really, really nice conformal junctions out of it. And the benefits are then that you only need a very small amount of material. You get super high coverages of like 95% of your substrate. And you can do this onto basically any substrate as well. The downsides are it requires water. And I have that as a downside because sometimes some 2D materials are reactive with water. So the key points when it comes to inks and deposition are we have many, many ways to stabilize our nanosheets, depending on what process you're trying to do. They are compatible with basically every printing method that we can think of. The deposition itself strongly affects the structure of the network. However, post-processing techniques can alleviate those effects. And what we see as well, which is important, is that the structure of the network strongly affects the electrical properties. So that takes me on to the network properties themselves. So one thing that we find with two-dimensional materials is that the interparticle junction properties are much more variable in these ones than they are in 1D carbon nanotube networks or 0D metal oxide networks, for example. So the overlap area between two 0D particles, for example, it doesn't really matter how you orient the particles. The junction overlap is going to be basically the same. And it's quite similar then with 1D particles too. I mean, you can twist them a bit, but I mean, People have been trying for 20, 30 years to do alignment on these, and it's quite difficult. But when we look at 2D material networks, what we find is that depending on the sizes of the nanosheets, we get this kind of oblique alignment, as we call it, where it's like all these rigid disks or rigid bodies in a jammed system. If you have something like this, the junctions between the sheets themselves tend to be quite small, so we end up with low network mobilities. If you use this liquid-liquid interface method, we can align all the nanosheets up edge to edge, and we get a slightly better mobility out of it. And then if you do something like spin coating, or you do this liquid-liquid deposition technique iteratively, you can align the nanosheets up like this, and we get much higher mobilities out of it. So if we want networks with the properties of the nanosheets themselves, what we need to do is be very, very considerate about the junctions where they come into contact. So let me give you an example of why this is important, just very briefly. If we take a material like black phosphorus, this is a mobility of about 1,000. It's been theorized. But let's assume we have a material where the nanosheets have a mobility of 1,000, and the junction mobility, the junction resistance gives us a network mobility of 0.2. Then by just applying Matheson's rule, what we find is that the mobility of your network will be completely dominated by the mobility of the junctions. So it doesn't matter how good your material is. If the junction resistance is extremely high, you're never going to be able to hit these material properties themselves. So the proposition here is that the junction resistance is the key rate limiting performance parameter for your network. So the example I'm going to show you here is semiconducting networks, where the way these are typically characterized for transistors is the on-off ratio versus the mobility. Where we have a material like graphene down here, which obviously has the high mobility of the zero bandgap semiconductor, but for the same reason, it has very low on-off ratios. And spread across the rest of the graph here, we have the TMDs, the transition metal dichalcogenides. Now, what we've noticed is that in the last couple of years, MOS2 has started to show mobility values that are competitive with organic materials and carbon nanotubes. But if we look a little bit closer, what we find is that the electrochemically exfoliated nanosheets tend to perform much better than the liquid phase exfoliated ones. Now, if we actually look at the networks, the reason for this becomes very, very obvious. This is an SEM image of a liquid phase exfoliated network. What we find is that the nanosheets are quite thick. They're kind of jammed in and sticking out on top of each other. And when we look at the mobility of the nanosheet, it tends to be much, much higher than the mobility of the network. When we look at an electrochemically exfoliated network, I mean, the SEM alone tells you these sit very nicely on top of each other. The junctions are very obvious. And not only that, but the junction overlap areas are huge as well. So this is good for facilitating charge transfer between your sheets. For networks like this, what we find is that the mobility of the nanosheet is on the same order of magnitude approximately as the mobility of the network. So that's semiconducting networks. Does this also work, transfer over to conducting networks? Well, we took graphene. I took as many of the papers that I could find that reported conductivity and length statistics. And what we found is that there's basically no correlation here, as far as I can tell, on this graph. So you can have long nanosheets with high conductivity in your network, and you can have small nanosheets. So this means that length is probably not the relevant variable. So we found this paper here, which is interesting because they showed that the thickness of the nanosheet is far more important. So the mobility of the network actually decreases as the thickness of the nanosheet increases. So this means the thickness of the nanosheet is far more important, meaning if you go back to the length, this is probably due to low junction resistance because of their thin nanosheets. And this one's probably high conductivity because there's probably just a low number of junctions between the electrodes. So what is this about? Why do LPE networks have a higher junction resistance than the electrochemically exfoliated ones? Well, the reason is, as I showed you in the SEMs, the LPE nanosheets tend to get jammed together. They don't sit on top of each other very well, and you get these point-like junctions. Because the electrochemically exfoliated nanosheets are quite thin, they're able to conform very easily to each other, and we get these nice interfaces. And the way to understand this is, when is this possible? Well, what we do is we can just take a simple model system with parameters like the length of the nanosheet, the thickness of the nanosheet, the adhesion energy, and the bending rigidity, and then some arbitrary bending angle. And we find if we take the derivative, set it to 0, we calculate the total energy and minimize it. The result is only negative for some critical aspect ratio, some critical length and thickness. And what we find is that number is about 50. And for liquid phase exfoliated nanosheets, they tend to be much lower than that, which means we cannot get bending with these nanosheets. So is there another way to visualize this? Can we actually look at these networks and see what this looks like? And one way to do this is using FIB-SEM tomography, and then you can reconstruct we can reconstruct these networks using some software. So what you do is you take the FIB technique and you mill a section of your material, of your network, and then you image and cross section using the SEM. Then you increment about 15 nanometers. You do the same again. You mill away your material. You image. You mill, image, mill, image, mill, image. And what this does then is gives you 600 or 700 individual cross sections that have moved their way through the network. You can take image J, for example, and you can train image J to tell what is a pore. So what is not a nanosheet and what is a nanosheet. And then by creating these images that are binarized into simply nanosheets and simply pores, what we can do is we can reconstruct the network then by building up all of these images. So this is a network here of just the nanosheets with the pores removed, and this is just the pores in the network. And what we find is that the porosity is huge. It's about 44%, and every one of these pores here is connected. So this is one big macro pore basically inside of the network. And this is good for something like batteries, for example, where you have an electrolyte and you want it to be able to penetrate and access all parts of your network. So this is liquid phase exfoliated graphene, which is being spray coated. If we take electrochemically exfoliated graphene, we spray coat it using exactly the same method. What we find is that the network looks much, much better. The nanosheets conform to each other very well, and the porosity tends to be a lot lower. Another way of doing this then is using the Langmuir-Schaefer technique, this liquid-liquid interface technique. And this itself these networks just look amazing then. It just look, in some parts, it's like a reconstituted crystal. So something like this will be excellent for making transistors with, as the porosity is very, very low. We don't have many voids inside in our network. So the junction resistance here is clearly a key parameter. So the question is, we have this property, resistance, junction resistance, and can we measure it? Now, techniques for measuring the junction resistance tend to be very highly localized. We have conductive AFM, where we'll raster our tip along one nanosheet, and then we'll bring it across the other one across the junction, finding a very well-defined jump in resistance that can be measured this way. Another way to do it is with EBL, where we take two nanosheets that are slightly overlapping, and we deposit a lot of electrodes on them, and we can measure the junction resistance here across them by taking things like area. But the problem is, these are very highly localized techniques. If I have a device, if I have an entire network, these are simply not feasible. So we need a way to measure an entire network really quickly. So to begin with this, we did some modeling. So we do typical way that we do this with particle-based networks is you take a conductive path that goes across the sheets, and you take a resistor chain model where one resistor represents the nanosheet and one will represent the junction. However, because we want to measure this, what we did is that we noticed that, or we took the note of the fact that there will also be a capacitance associated with these junctions, which means that this resistor chain will actually be a resistor representing the nanosheet in series with a resistor representing the junction in parallel with a capacitor. So because there's a capacitance in here, this means this circuit will have a frequency dependence. So this means that we can apply a technique known as impedance spectroscopy. So this circuit model here is known as a Randall circuit. It's very well known, very well understood. It can be probed using these equations here, or it can be analyzed using these equations here. And we can perform measurements with impedance spectroscopy using a potentiostat or an impedance analyzer, and the measurement takes seconds. Now, two common ways to present this data are through a Bode plot, where we plot the impedance versus frequency, and the Nyquist plot, where we have the imaginary part of the impedance plotted against the real. So for a circuit like this, at low frequency, this capacitor will act like an open circuit, so the current will flow through the series and parallel resistor, meaning we can just read off the sum down here. And then, and on the Nyquist plot, then the resistance will be the sum of the series and the parallel. We just read it off the x-axis. At high frequency, the capacitor will act like a short, meaning current will just flow through the series resistor. And then to get the value of the series resistance, we can read off the high frequency end of the bode plot. And then where the semicircle meets the axis, then the offset will give us the series resistance. So the proposition, the way we modeled this was looking at our nanosheet junction system. The nanosheet will be represented by this resistor, the series resistor, and then our junction resistance will be represented by this one. Now, obviously, it's a lot more complicated than that. When we have our impedance output, we use our model to convert back into the actual network values. This is clearly going to be a distribution. They're not all going to be the same nanosheet resistance and junction. And the way we analyze this is with a bit more of a complicated equation. But the point is just to say, I don't have time to get into it. If you want to find out how we do this modeling, please check out our paper. But this means that we can extract junction resistances and nanosheet resistances. Now, what we find is that we can get the transport behavior of the nanosheet and the junction at exactly the same time if we do a temperature-dependent impedance method. So we do impedance at a range of different temperatures. This gives us junction resistance, which goes inversely with temperature, and the nanosheet resistance increases with it. So this means what we have here is behavior less than 200K, for example. We see 3D variable range hopping, and above 200K, we see activated transport, and that is behavior solely associated with the junction. When we look at the nanosheet itself, we see band-like transport. So this means that the nanosheet has more efficient transport properties than the junction. So let me visualize this for you. So imagine we have a carrier like an electron moving within our basal plane. This moves at a very efficient band-like transport process. When the carrier reaches the junction up here, it then has to hop between the nanosheets and between the layers, usually through 3D variable range or activated transport, which is less efficient than the band-like transport within the nanosheet. And then as it moves off into the next nanosheet, it moves off again at an efficient band-like process. So this means if we have a network limited by the junctions, what we need to do to focus on improving the network properties like conductivity or mobility to bring it up to a band-like process is focus on the junctions to reduce this junction resistance as much as possible to improve the properties. So the key points when it comes to network properties are the arrangement of the junctions is critically important if you want to have good properties in a network. We can do reconstructions then also using FibSem so we can visualize how much porosity is in there. And we can actually measure this junction resistance using impedance spectroscopy. So now that's been a lot of characterization. Let's move on to some actual devices. So I've shown you some transistors, I showed you some measurements. Back in 2014, we had this ugly transfer curve where it didn't really function at all as a transistor. Then over the years, we found vast improvements then in the cleanliness of a transfer curve, the mobilities have gone way up, and now high mobilities are routinely achieved and are published all the time now. So going back to this way of characterizing it, this on-off ratio versus the mobility, what we find is that the electrochemically exfoliated TMD networks, which are materials like MOS2, they are now competitive with the commercially mature metal oxides, carbon nanotubes, and what's important to note too is that metal oxides and carbon nanotubes, they tend to be reaching a ceiling on their performance. And with 2D materials, there's a lot of scope to go much, much further. And it's not going to be long now, I think, until we see a mobility of about 100 in some of these networks. So another device that we tend to make is these memristors. So when you have a memristor, the way it's often done is with an outer plane structure. So we take a bottom electrode, we take an individual monolayer of MOS2, for example, and we put it in on top of the electrode, and then we deposit a top electrode on top. Now, typically the way people take individual monolayers and place them is by mechanical exfoliation, but you can imagine if you have to make a wafer scale amount of devices, you're not going to be going around mechanically exfoliating each individual nanosheet and placing it because this is extremely tedious and it's a great way to lose PhD students. So a way to do it is by solution processing. So some of the techniques that I've told you. So we did this. We took a substrate, silicon dioxide. We deposited our adhesion layer of titanium and gold. And then using that liquid-liquid interface method, we globally coated the entire substrate in 2 layers of MOS2. And then we deposited our electrodes on top. So we were able to do this deposition in a couple of minutes. It was rapidly done. And then by depositing the electrodes on top, we had a memristor structure with high yield. So what we found was these functioned extremely well. We got large switching ratios of about 10 to the 5. The contact resistance, the on state was quite low, and we were able to operate at very, very low voltages as well. So we have these materials uh, composed of discrete networks. So this allows us to also work with printed strain sensors. Now, when you're talking about a strain sensor, materials are used are often things like copper, and they tend to have very, very low gauge factors. Now, gauge factor is just a method of how much the resistance changes when you stretch it. So what we did is we took our dispersions, we took our graphene inks, we printed them, and what we found is that as the network thickness increases, the conductivity increases because of percolation effects. So you can see here for low thicknesses of about 40 nanometers, we don't have a continuous network, so the conductivity is low. And then up above a certain thickness, the network becomes complete, and the conductivity tends to saturate then because we have a bulk-like regime. Now, what we found was interesting was that this gauge factor value shows inverse behavior. So at very, very low network thicknesses, when this is discontinuous, we get extremely high gauge factors up in the hundreds. Okay, so this is far beyond what you can achieve with a metal. So what this means is simply by tuning the thickness of our network and the conductivity and the piezo resistance themselves can be tuned over a very, very wide range. So we can take this property and we can make
Sorry, Dr. Kelly, to interrupt you.
Yes.
Sorry, you have 2 more minutes.
Okay. Okay. 2 more minutes.
Okay,
Great. Thank
because
you.
we
I'm
have
actually
a lot of questions from our participants to answer.
okay. All right. Okay, well maybe I'll
Thank
finish
you.
up on the electromechanical sensors. So we take our dispersion and we from the same one that we have in the sensors, the ones I just showed you, we mix it in with a polymer like putty, and then when we print it, what we find is we have extremely sensitive strain sensors. So this is Connor Boland here. He held a network like this up to his neck, and he was able to monitor his breathing, inhalation, exhalation. He also was able to monitor heartbeat. He was able to discriminate the dichroic notch on the heartbeat, and he found a spider in the lab, and he had the spider walk across one of these sensors, and he was able to detect the spider's footprints. So I do have some stuff here on EMI shielding, but just for the sake of brevity, I will leave it there. And I will say the take-home messages from all of this are these materials are easy to process. The deposition method itself strongly influences the morphology. The nanosheet thickness itself is a very important factor, and this influences morphology too. You really, really need to care about your junction resistance if you want to get high performance networks. And high performance is then possible across a range of devices. So with that, I'll say thank you very much for your attention. And yeah, I guess I'll take questions now. Thank you.
Thank you so much, Dr. Kelly, for this great presentation. I will now start reading the questions from our attendees. So the first question is, how do you attach the crystal to an electrode?
Very simply, you just clamp it. You can
Okay.
do something like you can take a copper crocodile clip, but the pressure tends to be quite high in the crocodile clips. So maybe you're thinking the crystals are quite small, but they tend not to be. You can get quite large crystals, the size of your fingernail, maybe, and you can just literally just clamp it with a crocodile clip. So it's that simple.
Thank you. The next question is it possible to adjust the band gap of nanosheets made through liquid phase exfoliation for specific applications such as photovoltaics?
Yes, it is. So the band gap of some materials is thickness dependent. And what you do is, after we have our polydispersion, after you apply the liquid phase exfoliation process, you will have a dispersion with materials with lots of different thicknesses in there. And what you do then is the cascade centrifugation technique, where you do iterative centrifugation steps, and then the sediment in there will have nanosheets of different thicknesses. Now, depending on how closely together you put the centrifugation trapping speeds, this will change the distribution of your thicknesses. So if you want a very, very specific tight band gap, nanosheets that are very, very close together in band gap, you will have to do very, very close centrifugation speeds. So the way to do it would be to process your material using sonication, and then you would have to choose centrifugation speeds very carefully. And I would suggest looking up Claudia Bacchus's paper on cascade centrifugation to give yourself an idea of how to do it.
Okay, thank you. Another question is, when a surfactant is used for stability, is there any possibility of reduction in the surface area of nanosheets?
So I presume the question there is it going to change the properties once it's deposited in the network? And usually what we want to do is actually get rid of the surfactant afterwards because we want the properties of the material, right? We don't really want to be changing their properties. So after you've deposited your network, there will be surfactant in there. What you can do then is just soak it in water overnight, for example, and you will remove basically all of the surfactant that way. If you have electrochemically exfoliated nanosheets, for example, and they're on a substrate, because they're quite large and thin, they adhere quite well, and you can usually just wash it then with IPA or something. So it's easy to remove these surfactants so you don't actually change the surface areas of surface energies of your materials.
Thank you. How waste biomass can be converted into nanopowder, which is then synthesized to develop suitable potential material of use like carbon capture, biomedical application. For example, nanofiber from biomass.
Well, like maybe the answer would be, I mean, like you can apply these solution processing techniques, obviously, because cellulose, for example, materials like this are dispersible in water, they're dispersible in a range of solvents. So the question would be, how do we want to process it? Do we want to break up the fibers? Do we want them to be a certain size? The selection techniques will work as well with a range of different materials. So maybe is the question like, do you want to change the properties of material in terms of dimensions? And I would say solution processing techniques will do this, but it depends on really what you want as a final material. So the answer is yes, but I mean, it's a specific question I think you need to ask.
And another question is, how can the coverage area of electrospinning be scaled up to achieve larger surface areas while maintaining uniformity and quality of the deposited nanofibers?
So, sorry, did you say electroplating? Well, I think like with electroplating, you because you have generally a very flat electrode.
Electrospinning.
Oh, electrospinning. I beg your pardon. Okay. Um, well, I'm not very familiar with the electrospinning technique myself, so I'm afraid I won't be able to offer any insights on how to improve electrospinning. If you want to talk about solution printing, I'm happy to discuss that.
Okay, thank you. Are there any assumptions for the drastic jump in conductivity?
Well, the reason for these jumps in conductivity, some of the ones that I showed, are typically percolation effects. So the dominant effect here is going to be the thickness of the network. And what we find is that, once you're in the percolation regime, it depends then on the thickness of the particles themselves. And this is the characteristic that you want to control then to modulate your conductivity over orders of magnitude in the percolation regime. So again, like nanosheet thickness would be the factor that you'd want to consider there.
Thank you. And are there any assumptions? Sorry, I asked this question. How can we validate junction resistance by simulation or fitting?
Well, I didn't show it to you there. We actually have a model where we relate the junction resistance itself to properties like nanosheet length, nanosheet thickness, carrier density, network conductivity, porosity. So if you want to actually do this and simulate it, if you look at our paper in Nature Communications, we will show you exactly how to do that. And we have something like 93 pages of supporting information. So the answer will be in there.
Great. And one last question. When different atoms are used for intercalation instead of lithium, how does the surface and electronic properties of the nanosheets evolve?
Oh, so this is why we actually use the bigger nanosheets, because we want to minimize charge transfer from the cation to the crystal itself. So the larger the cations, then the fewer will actually go in, and the lower the amount of charge transfer, and you can retain the properties of your nanosheet without actually changing them. So I don't think it's actually very well understood the relationship between diameter and monolayer yield, for example. But if you use a bulky cation, ones that are, maybe 10 angstroms in diameter, you won't change the properties of the nanosheet. And we've been able to replicate MOS2 monolayer properties using these cations. And that's reflected in something like photoluminescence, because that will only happen in monolayers and it won't happen in 3, 4, 5 layers. So exfoliating using these bulky cations, we retain the monolayer properties because they're so large that you don't get enough charge transfer to the material to change it.
Dr. Kelly, I would like to once more thank you for accepting our invitation to participate in the webinar series of Informative School. It was an honor to have you, and our participants seemed really interested in your presentation. So I will now stop recording.